Hi everyone, and welcome to a new video about LC ladder filter design. This is our example number 4 where we'll discuss the bandpass filter for our elliptic response. We will discuss the specifications and also work out the calculations step by step and also verify these in SPICE simulations. So our objective is to set an elliptic response which must be an LC ladder configuration for a bandpass filter. We will use a 50 ohm double terminated shunt input circuit. That means actually the following. Looking at this generalized filter block, we have an RS and RL, that's the source resistor and the load resistor. They are each 1 ohm in the normalized values. We need to scale it up later to 50 ohm. That means we need to have a magnitude scaling factor of 50. In addition, we have these specifications. We see the maximum passband ripple, minimum stopband attenuation. The values are shown in, or also the lower and the upper passband frequency and the lower and the upper stopband frequencies. And we will verify these also later in the SPICE simulation results. So let's look at our solutions step by step. The first step is looking at the passband bandwidth and also the center frequency from the specifications. For the passband bandwidth, we use the upper and the lower passband frequency in omega, so we need to multiply each of these by 2 pi. We have actually now this expression, and it will give us 9 pi times 10 to the power 5 radians per second. The center frequency is the geometric mean of the upper and the lower passband frequency, which is again in omega, so we have then the 3 pi times 10 to the power 6 and then 2.1 pi times 10 to the power 6. And then we have this 7.885 mega radians or million radians per second. Okay. Now that's our step 1. Step 2 is calculate the normalized passband frequency and also the normalized stopband frequency. We will use this shortly in the future steps, and this will be now done for prototype low pass filter, because we will do in the later steps also the transformation from the low pass to bandpass filter. Now our normalized passband frequency in the capital letter omega is given by this expression. You see again the difference between the upper and the lower passband and then divided by the bandwidth we just calculated. And this is actually always 1. This is just for completeness here. The stopband, normalized stopband frequency is given by, again now this time, the upper and the lower stopband frequencies, the difference with that, divided by the bandwidth which is determined here in step 1. In this case we get 1.2778. And now we will use this shortly for our determination of the filter order. Step 3 is the bandpass scaling factor, K sub F bandpass, and that is just omega bandwidth, which is 9 pi times 10 to the power 5 radians per second. So this is a value we will use shortly for our scaled up component values. And it's also 450 kilohertz. Now step 4 is the filter order, one of the important steps, and there's the required transition sharpness is there, one of the important parameters. That is determined from step 2 information, because we know that the transition sharpness given by capital letter omega r is equal to the normalized stopband frequency divided by the normalized passband frequency, which is 1.2778. And this is an important value. We need to also use the minimum stopband attenuation, which is 19 together. So these two values we need to use in order to determine what the order of our filter must be. Now the filter table for the elliptic response is quite lengthy and large, so it is almost difficult to discuss this here in great detail. And what I have seen is, by looking at the tables, this is now produced actually a part of it, is that a third order filter will do the job. Why? Because if we look at this region, and when I now make that clear by this shaded region in yellow, you can see here, because this is the normalized or the required transition sharpness, and here you have what you get as any A minimum for this ripple, because we had 1.2494 dB as the ripple. You see here the 1.2690, which is smaller than that one. That is actually what we need, because this is the maximum allowed transition sharpness. And there you see here 19.82. If we go up in this row, the sharpness goes up, so that is actually not according to specifications. Of course, the A minimum is going up, so this is better, but we do not fulfill the omega R. When I go down, row 31, that's fine, because you can see that this is even better, but you get lower A minimum, still above 19, and if we go even lower, the sharpness will be even better, but we have now 18.66 dB, which is not sufficient, so we need to have 19. But let's zoom in here in this part of the table. So that means we already know that we need a third order, but it's good that we also zoom in the part where we talk about, which is then between the 29 and the 32 row. You see, actually I actually made a bold one, which is what we used shortly, but this part here, in order to satisfy both the maximum omega R and the minimum 19 for A minimum, we can choose between 30 and 31, row 30 and 31, because going up means I cannot fulfill any more the omega R, and going down to 32 I cannot fulfill any more A minimum. So in this case we just choose row 30. You can also go for row 31, it doesn't matter, it's just perfectly fine. Okay, and these are the component values normalized we will use shortly in the future steps, and this is what we will use. Okay, going on, and then also collecting the values we just determined for omega center, the bandpass scaling factor, and also the magnitude scaling factor, which is discussed because we need to go from 1 ohm to 50 ohm. Now, this is also one of the important steps, because we need to make now the low pass to band pass filter transformation, the circuit transformation. This is the low pass filter for our elliptic response. We see the C1, C2, C3 and the L2. You see that also in the table, so we see actually also what these values must be in a normalized value, because C1 is just this, 1.6674 farads. That's also for C3. And C2 is this value, 0.8995. And L2 must be 0.5742 Henrys. But this must be transformed to a bandpass filter. What does it mean? That means actually following, you replace each capacitor by a parallel capacitor and an inductor, and each inductor must be replaced by an inductor in series with a capacitor. Now I designate the P for parallel and S for series. So this must be transformed in this circuit, which is then now a larger circuit, so we get actually twice as much, except this R and L. And now we also scale up. That means the R and RS and RL will be scaled up. That is given by this prime here and also here. And you see here the CP parallel because of C1, and LP C1 because of, again, due to C1, and similar for C3. And I also see that for C2, that's shown here, these two. And now L2, the inductor, will be a series combination of the capacitor and inductor according to this transformation. So our circuit we need to use is this one given here in green boundary. So let's bring it here and now calculate this scaled component values. That is for our final form of our circuit. And these are the values, parameters we need to use to calculate these parameters. The first one, CPC1, is equal to C1 from the table divided by the Km and the KFBP, which is here. So we do that and we get our 11.79 nanofarads. Now for the LPC1, you get also a formula which is similar to actually what we have used in the previous examples. You see that again, omega center squared, C1 again from the table, and also the Km and the KFBP. And that is then 1.364 microhenries. In a similar form for CPC2, but now you get this coefficient, so the only change is just the coefficient, so then the new value is produced here, and also for the LPC2 in a similar form. Now the CPC3, looking again here, but that's the exact same as CPC1, and LPC3 is exact same as LPC1. The final one is for this series combination. So this is the formula. Now we have to use the omega center there, and I get now this value, and for the inductor you get now this formula, you get now this value. The final two is really the RS prime and RL prime. They're just 50 because we need to go up from 1 to 50 ohm. So that's actually shown here, and also for the load. Okay, that's all complete. So we have now all the component values for our final design. Let's bring them together here. This is the summary, and let's also look at the designed circuit here in the simulator. The first one is our prototype circuit, which is our prototype low-pass filter circuit. You see the C1, C2 from table, and also the C2 also in L2, again from the table. You also see here in the in below, that is the scaled up final bandpass filter circuit, and also the values here. So you see the 11.79 here, also 11.79 there, 1.364 microhenries. That's actually here. It's also here. You also see here the series capacitor because of L2. That's shown here. You also see here the series inductor because of L2. That's shown here. So everything's also shown here because of the RS and RL. They're all scaled up to 50 ohms. Now we need to simulate the circuit for this circuit and then see what the response is and if this is really according to specifications. So let's go to the simulation results in SPICE, and this is the Bode plot. You see here actually the following. Before we go into the detail, what we see here in the labels, that there's a ripple in the passband, and there's also a ripple actually in the stopband, which is a characteristics of an elliptic response. So there is actually ripple in both regions, passband and stopband. So what we see is the following. We see the passband value here, 1.05 megahertz, one of the important frequencies. We see a gain of minus 7.2753 dB, and we have a baseline here, which is our center frequency at this minus 6.0206 dB. Why is this minus 6.0206 dB? Because the gain at the passband is 0.5, because it will be 50 ohm divided by 50 plus 50, which is then 100, so 50 over 100 is 0.5, and in logarithmic scale, that will be then 20 log of the 0.5 will be then minus 6.0206 dB. And this center frequency is also what we have calculated actually, so this is also correct. And why is this correct? You can say if this is correct, you can see that the baseline is this one. You go down here to minus 7.27, and that is a decrease of approximately 1.25. It is close to what we actually needed, so it's maybe hair larger, but the maximum allowed passband rule was this actually 1.2494, so we are really close to the according to specifications. Looking at the upper passband frequency, you can also see that actually here and here, these are really close to each other, so we can also see that this is also very close to what we needed. The next label is about the lower stopband frequency. That's at 1 megahertz, which is this one. And now you see here that their gain there is minus 26.76 dB approximately. So going again from the baseline, you go down by 20.74 dB, but we needed at least 19. So again, this is according to specifications. The upper attenuation, stopband attenuation is then 20.68 here. So again, much actually higher than what we needed. We also see here some notches, so at notch frequency here and notch frequency there, so you get actually more notches if the order goes up. What you also see is, again, as said before, the center frequency is 1.255 megahertz. And that is according to specifications also because the omega center was 7.885 megaradians per second. When you go to the frequency in hertz, you divide by 2 pi. That means you get now this value, which is exactly as we have here in the simulator. What you also see is, which is interesting, that the gain goes up actually because of this notch again here, and it stays actually below some value, and that is 19.82 dB, which is actually what we also have seen in the table. So in the table it was displayed that the minimum attenuation you should get for these choices of the components is 19.82. So again, still lower than 19. So that is also fine. That means we have achieved our goal and also designed this circuit according to specifications. All right, This is our example number 4, discussing the bandpass filter design using the LC ladder filter configuration for our elliptic response specifically. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.